Hi there, welcome to this lecture series on matrix algebra. Today we cover lecture 10 and this is part 1. The topic is linear combinations. Let's get started. Let's begin with introducing the concept of the linear combination. It's associated with a vector space, so let V be a vector space. Then the term linear combination of a set of vectors v1, v2 and vn, n of them, they belong to the space capital V. So you take n vectors and you select coefficients. These are just real numbers, c1, c2 and cn. And you form a new vector, which is these vectors v and multiply by some real number coefficients. So a linear combination of these vectors is just another vector that can be written like this. And then if you have a given set of vector v, and you see that you can choose different coefficients to form a different v. So now we can form a set of all possible linear combinations that can be obtained by this form for this given set v. Then that set of all possible linear combinations is called the span of the vectors v1 to vn. So here's a notation. We will write like this. Span of v1, v2, vn. What is it? Well, it is a set of these vectors c1 plus c1 v1 plus c2 v2 plus cn vn, and where the c1, c2 and cn's are just real numbers. Okay, let's take some examples. In the first example, let's look at the space R3 and we consider two vectors. V1 is a vector that's 2, 0, 0, and V2 is a vector 0, 3, 0. So what's the span of V1 and V2? Well, by definition, the span of it will be the set of vectors where V1 is multiplied by C1 and V2 by C2 for any C1, C2 in R. Okay, and then we see that this one multiplied by C1, you get 2 C1, 0, 0. And this one you multiply by C2, you get 0, 3 C2 and 0. And you add these up, you see that you have some elements on the first and on the second position, but the third position here, it will be always 0, right? So this becomes a set of all vectors where the third element is 0 and the first and the second, they are just real numbers. Okay, so we can also say that this is the subspace of all vectors v in R3 whose third component is 0. Now let's take a second example. In the space of continuous functions, let's consider three functions. F of x is 1, that is the constant function which is always 1. And then g of x is x, and h of x is x squared. And then the span of these three functions, f, g, and h, that is the span of 1, x, and x squared, would be the set that a linear combination of these three. So we multiply the first function by c0, and the second one by c1, and the third one by c2. Okay, so and add them up. So a function looking like that, where c0, c1, c2 are real numbers. Then we see that this is exactly representing all polynomials of degree less than equal to 2. Now let's look at an example for a vector space with the matrix as element. So let's say the space V is all 2 by 2 matrices, and then we consider two particular matrix, A1, which has just 1 as this first element, and then A2 is 1 at the element in position 2, 2, which equals 1, and everywhere else they are 0. Then the span of A1, A2, well, we can write it out. That will be the linear combination of A1 and A2. So it's C1 times A1 and plus C2 times A2 for C1 and C2 in R. Okay, let's multiply it in and add up. So I get C1 here, and I get C2 here, and you add up these two matrices, and then you will get a diagonal matrix, 2 by 2, which has C1 and C2 on the diagonal, and C1 and C2 are just any real numbers. Then you see this is the set of all 2 by 2 diagonal matrices. And we have seen that earlier, that this is a vector subspace. Now here is an important theorem. It says that for any vectors in the vector space V, so V1, V2, and Vn, they all belong to V, then the set W, which is the span of these vectors V1, V2 to Vn, that is always a subspace of V. Okay, so let's try to prove it. Okay, so here's the little proof. Let's consider two linear combinations. Let's call them V and W. So if these are linear combinations, then they're in the span of these vectors, so they will belong to W. W is the span. Okay, let's say V1 is written as a linear combination with coefficients A1, A2, and An. And W is a linear combination with coefficients B1, B2, and Bn. So we need to show that W forms a subspace. That is, we need to show two things. And we need to show that V plus W is in W, and we need to show that C times V is in W. Okay, let's verify the first property here. So what's V plus W? We can add up these two functions, and then we see that we can combine like terms with the V's. So V1 now will have coefficient A1 plus B1, and then V2 will be A2 plus B2, and so on and so forth. And then we see that this is again a linear combination. So it's in the span of those vectors, so therefore it's in W. And then the second property, C times V is in W. Let's look at C times V. Well, then you just take the V and multiply by C, and you see you can multiply C on every turn. And then V1 now will have coefficient CA1, and then V2 will have CA2, and so on. And we see that this is just all real numbers in front of the V's. So again, it's a linear combination of the V vectors, and therefore it belongs to W. Okay, so that proves that the W is actually a subspace. So the linear combination now leads to a definition, a very important one is called linear independence. So it's the following. We say that if we have a group of vectors v1, v2, vn, we call that they are linearly independent if the following is true. That is, the only way to achieve that this linear combination equals to a zero element is to choose all the coefficients to be zero. So we remark that if you choose all the c's to be zero, then no matter what the v vectors are, this is always zero, right? So a a linear independent set of vector has the property that that is the only choice of coefficients that will make this sum 0. So, on the other hand, now if for some coefficients C1, C2, Cn, not all 0, it's very important, we can find one set such that this equals 0. So this is like otherwise, not in the linear independent case. So if that is the case, then we say that this set of vector, they are linearly dependent. Okay, so let's take some examples, get us familiar with this concept, linear dependence and linear independence. Okay, so in space R2, let's consider two vectors, v1 and v2. Are they linearly dependent or are they linearly independent? Well, actually, we need to show they're linearly independent. Okay, so we can follow the definition and then form this vector C1, V1, C2, V2 for any C1 and C2. And if we write it out and put the V1 and V2 in, and then add them up, and you get this vector. And then we set this to be the 0 vector, and we try to find solutions for C1 and C2. And if we find that there is a unique solution, C1 equals C2 equals 0, then this is linearly independent. Okay, so let's do that. So we set this to be 0, the first element, and we set the second element to be 0. And we can easily solve C2 must be 0 from the second equation. Put that one to be 0, you conclude C1 is 0. And that is a unique solution. Therefore, there's the only solution and that fits the definition of linearly independent vectors. Okay, now a second example, let's look at two vectors and can we show that they are linearly dependent? Well, to show they're linearly dependent, we could just find one set of coefficients C1 and C2 such that the linear combination becomes 0. Okay, so let's see if that's possible. So again, we write this out, C1, V1, C1, V2, put in V1, V2, and add them up, and we get this vector, and we want them to be a 0 vector, and we see if we can find C1 and C2. Okay, so that means the first one is 0, and the second one is 0. And let's take a look at this, and we see that if I take the first equation and multiply it by -2, I get the second equation. So the second equation actually is redundant. That in principle, I only have one equation here. And in fact, one can easily find a solution. We can say C2 is 1, C1 is 3, will make both equations 0. So therefore, this is a solution, and the elements are not all 0. Okay, so therefore, these two vectors are linearly dependent. Okay, another example. Let's say in R2, we have 3 vectors. V1 is like this, 1, 0, and the V2 is 2, 3, and V3 is 0, 1. And we want to show they are linearly dependent. Okay, and then we only need to find a set of coefficients C1, C2, C3, not all 0, and the linear combination becomes 0. So we see that this is 1 and 1. So if we make the second element multiply by -2, and then we multiply the first one by a 2, then you add up, you get the first element 0. And then if you take the third element and multiply by 3, then you get 3, and this is -3, and it's 0. Therefore, we see that we have this. So C1, C2, C3 are the coefficients here, and the linear combination is a 0 element, and the coefficients are not all 0. Okay, so these 3 vectors are linearly dependent. And actually, we can put a more general remark, that is, if you're in space R2, that is vectors of 2 elements, then when you pick any 3 or more vectors, and they are always linearly dependent. Okay, so one more example. Let's consider the space of continuous function, and with the 3 functions, fx is 1, gx is x, hx is x squared, and we want to show that they are linearly independent. Okay, so basically we can follow the definition, and let's form a linear combination of these 3 with coefficients c1, c2, and c3. And if we want this to be 0, that is a 0 function, which is the function is identically equal to 0 for any values of x. Okay, and then what does that mean? Okay, let's put it in the function f, g, and h, and then we'll have c1 plus c2x plus c3x squared must be 0 for every x. And let's see, is it possible to find the coefficients c1, c2, and c3 here? Well, one way one can do would be we can take different values of x, because this equation holds for every x, right? So we can take different values of x, and then we'll obtain constraints for the coefficients, equations for them. So let's try 3 values of x and take x to be 0, and then we have c1 equals 0. Now take x to be 1, then you get c1 plus c2 plus c3 is 0. And then you can take x is -1, then this is -1, and that's 1. Then you get c1 minus c2 plus c3 is 0. And you can solve this. So it's an easy one to solve. So you get c1 equals 0 from the first equation. Then you cross out these, and you have c2 plus c3 is 0, negative c2 plus c3 is 0. You can quickly solve them by adding this two equations up, and then you will get c3 is 0, and you subtract them, you get c2 is 0. Then we see that the only possible choice would be c1, c2, c3 is all 0, and therefore we can conclude that the function f, g, and h, like that, they are linearly independent. Now let's take an example of functions that are linearly dependent. So we have 3 functions. F is 1, g is sine square, and h is cosine square. And we want to show they are linearly dependent. So we just need to find a set of coefficients c1, c2, c3 such that the linear combination of these 3 functions becomes 0, and those constants, those coefficients, are not all 0. Okay, and we observe that g and h has an identity. So sine square plus cosine square is 1. So sine square plus cosine square minus 1 is 0. So comparing this identity to our function, we see that the first one will be -1 times f, and then the second one is gx, and then the third one is hx. So this is a linear combination of these 3 functions, where c1 is -1 times 1, and c2 and c3 is 1, because of rewriting this in this way. Okay, so we have found a linear combination of these 3 that ends up in the 0 element, where the c1, c2, c3s are not all 0, and therefore the 3 functions are linearly dependent. Okay, so that is all for the first part of this lecture, and then what follows will be we'll be using these linear independent concept and to form what we called a basis for a space. Okay, so I hope you enjoyed this one. I'll see you soon.